The topic of today is forces of nature. First, let us say a few words about what we mean by the word interaction. Interaction means exchange of forces between two bodies or objects or particles or even two waves, one coming into another's way, be it a collision or superposition or overlapping or whatever, and being in proximity, they influence each other. We say that the two objects or entities meet and interact, that is, exchange forces. Now let us present the classical picture first. Here Q prime is the source charge and said to be interacting with a field charge Q through the field E that it has set up around itself. The field charge Q gets a feeling of the presence of the source charge Q prime, and in the process gets repelled or attracted depending upon the sign of the two charges. The quantum picture is a bit different. Here the source charge Q prime is said to communicate with the field charge by emission of a virtual photon. So these two charges talk to each other through exchange of a mediator called photon. Now, what is important is that the field in classical picture is not directly observable. The virtual photon in quantum picture is also not directly observable. What can directly be observed is the force. Force is a measured quantity. The basic interactions of nature are listed over here. One is strong interaction, electromagnetic interaction, weak interaction, and then we have gravitational interaction. We'll discuss about these in details now. Let us first study where do we find these four interactions. In other words, which phenomena represent which interaction. We'll first take up gravitational interaction. Gravitational interaction is an everyday manifestation. It presses us into the ground, however much we wish to fly or float in air. Not only the proverbial apple, but all fruits, in fact all objects, fall down to the ground. The planets, like our Mother Earth, revolves around the sun. All motions we observe in our solar system and the galaxies, the motion of satellite, asteroid, motion of comet, is due to gravitation. Gravitation has a role in the motion of projectile, whose equation of motion involves g, and the solution also involves gravity. So the large-scale structure of universe and the macroscopic phenomena are due to gravitation. Tides are due to swelling of water bodies due to moon's gravitational attraction. Also, formation of sun stars is due to compression of interstellar gas and dust, and the intergalactic matter are drawn together due to gravitational pull. They condense and we get stars. Again, Stars form galaxy, and they are within the galaxy due to the gravitational attraction. They do not leave the galaxy and move on. Perihelion of Mercury or any other planetary system precesses to cope with or negotiate gravitational force and has to balance to keep moving on. Barring atomic and nuclear scale or dimension, gravity has a significant role. Now comes electromagnetic interaction, which has a number of everyday manifestations. We see each other with light. You are listening to this lecture using lasers in computers and so on and so forth. All these are manifestations of electromagnetic interaction. When someone flexes muscles or shakes hands or picks up something or say kicks a football, muscles are contracting in the molecular level. It is the bonds that are being arranged and rearranged in a variety of ways. Again, bonding of molecules and atoms are due to electromagnetic forces. So all such activities of our body, the muscle forces and so on, are exhibitions of electromagnetic interaction. We all know magnet attracts iron, exhibiting magnetism, and magnetism is related to charges in motion. So are currents. Again, transition of atoms or electrons or charges from one state to another state gives rise to what we call atomic spectra. Now these are glaring examples of electromagnetic forces. Binding of electron nucleus to form atom and then molecule, and then solid, liquid, gas, crystal. There are various types of properties. Some is hard, some is soft, some is elastic, some has less elasticity, some exhibit optical property, etc. All are manifestations of electromagnetic forces. Pair production, pair annihilation, these are interactions involving photon. The decay of neutral pion also involves a photon. So it's an electromagnetic decay. Nuclear decay sometimes involves electromagnetism, like gamma decay, which involves emission of gamma due to transition of an excited energetic parent to a lower state to become or to be called a daughter. We use electromagnetic spectrum in our daily activities in a variety of ways. Either we click our camera to take a picture, speak in a mobile, listen to a radio, or see a movie in our TV or computer. These are all electromagnetic interactions. Having given examples of electromagnetic phenomena, let us now come to strong interaction. Protons are positively charged particles, and an assembly of protons will be repulsive and would disintegrate. Protons stay away from each other. Protons cannot be kept together, they will move apart due to their repulsion. But in a nucleus, of an atom, the protons are held together. They are forced to stay put. Their electromagnetic repulsion is overshadowed and reduced to insignificance by strong force. In a nucleus, multiple neutrons and protons stay together and they are kept bound by nuclear force or strong interaction. So it is strong interaction that is responsible for stable existence of nucleus, with which atoms are built and with which we all are made. So proton and neutron are bound through strong interaction in a nucleus. Again, the protons and neutrons and some other elementary particles are built out of some constituents called quarks. We will not discuss them here and we will do so in a later lecture. Now the three constituent quarks U, D, D are tied up together to form a neutron. U, U, D, they are tied up and a proton is produced. Strong interaction forces three S quarks to build an omega minus, another elementary particle. U and D bar are bound. They interact in such a way that a pi plus or a positive pion is produced. So strong interaction occurs between quarks. Certain interactions have been observed, like high energy scattering of nucleons by nuclei, the alpha decay, or a delta plus becoming a proton and a neutral pion. Here the transition of initial state, say delta plus, to the final state proton plus neutral pion occurs through strong interaction. Other examples involving nucleus, like generation of nuclear power or nuclear energy, which are helped by strong interaction. Nuclear fission, on which is based an atom bomb. Nuclear fusion, on which is based a hydrogen bomb. The nuclear weapons, that is situations involving high energy release, also energy production in stars, all owe to strong interaction. They are due to strong interaction. Lastly, let us come across to weak interaction. The most common example of weak interaction is beta decay of a nucleus, which we will do in the class of nuclear physics. Beta decay involves a transition between two isobars. This is the parent, this is the daughter, and they are isobars because they have same mass numbers. So beta decay involves transition between isobars and emission of beta particles, which are electrons or positrons. We won't elaborate on this in this class. Clearly, these decays like beta minus decay, beta plus decay, electron capture, as well as the muon decay, these are examples of weak interactions. Here muon is another elementary particle. Kaons, hyperons, which are called strange particles, they too decay via weak interaction. In this lecture, we are concentrating on the interactions, their nature, their characteristic, and we will present all these in a tabular form. And regarding elementary particles, we will be discussing in a separate lecture. The weak interaction has a significant role in the fusion of proton and neutron, and the punched state is a deuteron. And here a proton has been converted to a neutron and then punched with this proton. And this is possible only because of weak interaction, this conversion. Without weak force, there is no nuclear fusion inside Sun. Now, who can take part in these four interactions? In other words, what decides which interaction will occur? What qualifies a phenomena to choose a particular interaction? This will be discussed now. We first take up the case of gravitation. Anything that has mass, anything that has energy can show gravitation. Now, what about electromagnetic interaction? It's equally easy to predict. Anything that has electric charge can show electromagnetic interaction, that is, interact electromagnetically. Let us give an interesting and useful information here. One is, all elementary particles except neutrino and antineutrino take part in electromagnetic interaction. They do not take part in electromagnetic interaction. The other interesting information is that whenever in an interaction we find presence of gamma, presence of a photon, then that interaction is an electromagnetic interaction, provided it occurs. Now let us come to strong interaction. Particles having strong color charge qualify for strong interaction. Just as electrons, protons have a very important or intrinsic property which is called electric charge, similarly some particle, the quarks, the gluons, are characterized to be possessing a property called color charge, which enables them to take part in strong interaction. We shall discuss color charge in a later lecture, but let me add that this color charge is not the red color, blue color, green color that we see with our eyes. Now, the interesting and useful information here is that particles which take part in strong interaction are called hadrons. Secondly, leptons, like electrons, muons, do not take part in strong interaction. We shall speak of leptons in a later video, but let me mention that leptons are a group of particles, light particles in general. Next is weak interaction. Particles with non-zero weak isospin, which is a quantum number, take part in weak interaction. An important information is that neutrino and antineutrino take part only in weak interaction. Presence of neutrino or antineutrino in an interaction ensures that it is a weak interaction, provided the interaction occurs. We shall put all our statements in a tabular form at the end of this lecture. That will be an extremely useful information. Next, let us come to the nature of these interactions. While gravitational interaction is always attractive and charge independent because mass is positive, it cannot be negative. In contrast, electromagnetic interaction is charge dependent, may be attractive or repulsive, since there are two types of charges, positive charge and negative charge. Strong interaction is overall attractive. It is strongly attractive for distances of the order of Fermi, but it has a repulsive core. In fact, any system should have such a provision of repulsion in order to maintain its individuality, in order to have its own independent existence and extension. That is to maintain size. This is very important. But it is overall attractive. We cannot discuss these things in further detail in this lecture. Let us come to lifetime of these interactions now. Now first, let us focus on what we mean by a lifetime of an interaction. Lifetime of an interaction refers to the period of interaction, the time needed for some interaction to produce its effect. Strong interaction. The decay delta plus 2 proton and neutral pion occurs over a period of time which is of the order of 10 to the power minus 24 seconds. The typical lifetime of strong interaction is 10 raised to the power minus 23 seconds, meaning thereby that strong interactions are fast processes. And mind it, fast means 10 to the power minus 23 seconds. Compared to such extremely short time span, some interactions occur slowly over a longer period of time, and they are accomplished through weak interaction. And the time span for these decays are 10 to the power minus 10 seconds. So weak interaction is a slow process. They have a slow decay rate. Now slow compared to that of strong interaction. Electromagnetic interaction such as pi0 decaying to 2 photons, 2 gammas, occur in a time of 10 to the power minus 16 seconds. Electromagnetic interactions have a typical lifetime of 10 to the power minus 20 seconds, meaning that electromagnetic interaction, like strong interaction, are fast processes. Strong interaction is faster, and weak interaction is the slowest of the lot. We now move over to a very important description of these interactions in terms of the carriers, the force carriers who are presumed to carry this interaction. Earlier, at the outset, we spoke of quantum picture, where we saw that two particles require a communicator or a mediator or an exchange quanta to communicate. Now strong interaction occurs between particles called hadrons. As we mentioned twice before, a neutron and a proton both are hadrons, and they interact through exchange of pions. So here mediator is a pion between hadrons that carries strong interaction, communicating between neutron and a proton, or a neutron and a neutron, or a proton and a proton, and so on and so forth. Again, hadrons are built out of quarks. So the constituent quarks within the hadrons, they too need a communicator, a mediator, or an exchange quanta. And it is said that according to Gell-Mann theory, which he gave in 1962, the quarks are tied up through strings which are called gluon strings. So gluon is the carrier of strong interaction between quarks, which are constituent of hadrons, which are particles which take part in strong interaction. And the gluons have these properties. We are not going into details. We are not going into elaboration of these things, just I am reading out. Gluons are neutral, having no electric charge, but they possess color charge. They are flavorless, spin parity is of this value, massless, and there are 8 types of gluons, and they are bosons. Weak interactions is mediated by particles called W plus, W minus, and Z0, which are intermediate vector bosons. They are massive particles having mass 80 to 90 GeV by c square. They have spin parity of this value, and we are not going into details, just mentioning the exchange quanta. The electromagnetic interaction is mediated by photon, which has these characteristics: speed that of light, massless, they are neutral, they do not carry any electric charge, and they are mediator between two charged particles. And now comes gravitation. We will not speak about it much, as indicated earlier. As per unverified theories, a particle called graviton might be a mediator between two masses, and it has these properties. Now we will come to the range of interactions. Range refers to the extent or the distance over which the force is effective. It's the distance which one must go near the source to feel the effect of the interaction. The source will be able to exert its influence to a larger distance, up to a larger distance, if the virtual quanta can travel a large distance. And this is possible if quanta has low mass. So one can relate the range and mass through this relation. So range should be inversely proportional to the mass of the carrier. For strong interaction, mass of pion, the mediator, is of the order of 140 MeV, and so the range is short because it is a massive particle that is exchanged. Weak interactions are mediated by a much more massive particles, mass being 80 to 90 GeV by c square, so range is shorter of this value. It was Fermi for strong interaction, and it is lesser than Fermi, 10 to the minus 18 meters for weak interaction. On the other hand, for electromagnetic interaction, the mediator photon, and in case of gravitational interaction, the supposed mediator graviton, they are of zero mass, they are massless, so the range is infinity. The same conclusion can be followed from Coulomb's law, because only if we put R infinity, the Coulomb force vanishes. Only if we put R infinity, according to Newton's law of gravitation, the force between two masses is zero. So these forces operate over the entire space, over the entire region, and there is no escape from these forces. as per these laws. So electromagnetic interaction, gravitational interaction, they are long range forces. They have effect up to infinity. We next come to the current laws of physics regarding these interactions. The strong interaction is described by the quantum chromodynamics, which is abbreviated as QCD, as enunciated by Gross, Wilczek, Politzer in 1973, that fetched them Nobel in 2004. And this QCD describes strong interaction between quarks and gluons. Here chromo refers to color, used firstly because quarks possess 3 color charges, and secondly because the force between quarks is called color force. The electromagnetic interaction is described by various laws. For instance, Coulomb's law in 1785, Biot-Savart's law in 1820, Ampere's circuital law in 1823, and the famous Maxwell's equations, which describe the entire electrodynamics, was given in 1865, around 1865. And the current theory is quantum electrodynamics, which is abbreviated as QED, and was given by Feynman, Tomonaga, Schwinger in 1940, for which they received the 1965 Nobel. Now QED describes interaction between light and matter and is an effective amalgamation of electrodynamics, quantum mechanics, and special theory of relativity. The weak interaction is described by theories given by Fermi and is known as Fermi's theory of beta decay, 1933, theories given by Li and Yang, for which they got 1957 Nobel, Gell-Mann, for which he was awarded Nobel of 1969, and the current theory is called electroweak theory, which is a unification of weak interaction and electromagnetic interaction between elementary particles. And this theory was proposed by Glashow, Salam and Weinberg in 1960, that fetched them Nobel of 1979. Gravitation was described by Newton in 1687, but in 1915 Einstein's general theory of relativity, which is a theory of space-time, simply made people to think of gravity not as a force but as a consequence of curvature in space-time, and the curvature is caused by presence of mass. Now this is not the topic of today, and we'll go over to the last characteristic, namely the strength of the 4 interactions. Let us consider 2 protons separated by 1 angstrom distance, and let us consider their gravitational interaction using Newton's law of gravitation. When things are put correctly, we end up with a force between the 2 protons to be 10 to the power minus 44 Newton. Let us now find the electromagnetic interaction between those protons. separated by 1 angstrom distance, and that we do by using Coulomb's law. And when things are properly evaluated, we end up with 10 to the power minus 8 Newton. And therefore, electromagnetic force and gravitational force can be compared, and the ratio is 10 to the power 36, implying that electromagnetic force is larger than gravitational force by a factor of 10 to the power 36. We next consider two protons separated by a distance of 1 Fermi and calculate the electromagnetic repulsion between them using Coulomb's law, which gives 100 Newton. Now this force tries to tear apart the protons, that is, tries to disrupt the nucleus. Now, can this repulsive force be prevented by gravitational interaction? That can be tested using Newton's law of gravitation to find the gravitational interaction between two protons separated by this distance of 1 Fermi. And when things are properly put, we end up with 10 to the power minus 34 Newton, which is hopelessly far from this value. So this is too small, and therefore gravitational interaction cannot prevent their separation. But we know that nucleus is stable, these protons are staying together. This means that this force, this repulsive force, is overcome by another force that keeps the protons together, and that force is strong interaction. So strong interaction that overshadows this repulsive force must be 100 times stronger than electromagnetic repulsion. So the ratio of strong force to the electromagnetic force is 100. Now, coupling constant represents the measure of how strong an interaction is. That is, it represents the strength of an interaction. There are certain formulae for coupling constants corresponding to the 4 interactions. We are not going into details, but it can be shown that the ratio of strong force to the weak force is of this order. Now these values might differ. Let us put together all the results regarding the strength of the 4 interactions. We have this ratio. If we take strong interaction to be 1, then the gravitational interaction is weaker, and it is of 10 raised to the power minus 38. And things can be rewritten taking force of gravitation to be 1, and if we do that, we'll have 10 to the power 38 for strong interaction, the other interactions lying in between. We have pointed out so many aspects, mentioned too many data in this lecture, and the best thing now is to collect and combine or collate them into a neat table, which I have done here. The table shows various interactions in the first column, and the corresponding data have been entered in other columns. And this is the first page. This is the second page. Next, we come to certain queries that are often asked in class. Why is gravity force neglected? Answer is, gravity force is too small. We saw it to be 10 to the power 38 times smaller compared to strong interaction. So in regions, that is in interactions of particle physics, where strong electromagnetic and weak interactions are active, gravitational interaction has no significant contribution. Also, in Large Hadron Collider, abbreviated as LHC, the energy is of a mammoth amount. And so, taking an insignificant force does not improve our calculation in any way. Neither will our prediction change even if we take gravity into account. Secondly, we really do not know how gravity operates on a smaller scale. The next question is, when shall we take gravity into account? If we consider the present structure of the universe, we can see that it consists of large concentration of masses, and also we learnt that gravity force has infinite range. So on a cosmic scale, gravity is important, it dominates and is the sole player. Why don't we have electromagnetic interaction coming in, since electromagnetic interaction also has infinite range? Now this is because there are no large concentrations of positive charge and negative charge. So even if range of electromagnetic interaction is infinity, electromagnetic interaction has no significant role on a cosmic playground. Strong interaction has most strength. Then why is it not taken into account in cosmic scale? As we know, put in a lighter vein, strength always does not guarantee everything. Here, strong force has strength. Put correctly, strong force exhibits its strength only over nuclear distances, and outside of it, it is zero. So no question of it being a player in the cosmic playground. Another important query which is asked is whether gravity has no role in the small scale at all. Now some theories, quantum gravity, string theory, theory of everything and so on and so forth, some theories which we are not going to deal with in this lecture predict that quantum gravitational effects appear in Planck era, when gravitational energy of a system is equal to the total energy of the system. But the problem is that there is no experimental support of such theories or claim, and we have to wait till a breakthrough happens for the final answer. Why is it that strong interaction is so strong? This can be guessed because when we put something in a small volume, then delta x tends to 0, and then delta p tends to be very large, and this is needed from Heisenberg's uncertainty principle, and so too much energy gets into the system. Another very important aspect that let us mention now, and we will be dealing with it elaborately in later lectures, is that strong interaction is most symmetric and obeys all conservation laws. It is a law-abiding interaction, but weak interaction is least symmetric and disobeys many conservation laws. Often this is difficult to understand to many. In our society, we have certain laws, and there are people who are perfectly law-abiding, and we call them good people or good guys. But there are people who do not care to obey some restrictions or laws that they do not like. they are preferential in obeying laws set by the authority. And we can put them into various categories depending upon their history of violation of rules or laws. And most importantly, it is not unnatural to have different sets of people or guys with respect to a particular subject or issue. Some will obey everything, some will obey in half, and some will disobey most of the laws. Here too, study of nature reveals that there are many laws in physics, and we can categorize the basic interactions of nature, the strong interaction, the electromagnetic interaction, the weak interaction, depending upon how many laws of physics they satisfy. It will be shown later that strong interaction satisfies all the laws, while other interactions like electromagnetic interaction, weak interaction, shows violation of laws. And weak interaction is the bad guy who disobeys most. There is no shocking thing about this, since if all interactions obeyed all the laws, then that means there will be only one interaction in nature. In a future lecture, we can address these things: unification of forces, time arrow, entropy. Let me end this lecture with a quote of Richard Feynman. "The work I have done has already been adequately rewarded and recognized. Imagination reaches out repeatedly until suddenly I find myself momentarily alone before one new corner of nature's pattern of beauty and true majesty revealed. That was my reward." Scientists always strive hard. A true scientist does not care much about the rewards and recognition, because his goal and sole aim is to recognize and interpret the beauty of nature, unravel the hidden truths of nature. And there are too many edges waiting to be recognized. Thank you.